Imagine a suspension bridge hanging in perfect, quiet equilibrium, suddenly disrupted by the relentless, driving force of gale winds. To model physical systems like this, we rely on a specific class of math, second-order linear differential equations with constant coefficients. A differential equation simply maps a function against its own rate of change. But an unforced system resting in a vacuum is different from a system actively being pushed. Mathematically, this active pushing appears as a forcing function on the right of the equal sign. This equation shows the general form of a non-homogeneous system. The terms on the left describe the physical properties of the system itself. Over on the right, the condition f of x is not equal to 0 represents our gale wind, the external force. To accurately map the position of the bridge at any given moment, our final solution has to account for two distinct things: the system's natural resting state and the continuous mathematical disruption caused by that f of x term. We assemble that two-part solution using the superposition theorem. This box displays the general solution framework for a non-homogeneous differential equation. The first section is the complementary function, yc, representing the system's behavior if the external force was turned off. But the theorem hinges on the isolated term appended at the end, plus yp. This is the particular integral. It is a highly specific solution that is entirely free of arbitrary parameters. It represents the exact mathematical response to the forcing function. This presents a distinct analytical challenge. We have to systematically deduce the exact form of yp without relying on any arbitrary constants to absorb our math errors. To find the true, full state of the system, we need a mechanism that maps the external force directly to a specific, constant-free solution. We achieve this mapping using the method of undetermined coefficients. The core premise here is elegant. We make a highly structured, educated guess about the shape of yp. We base this guess strictly on the mathematical family of the forcing function, f of x. Take an exponential function like e to the x. Its derivative cycles back to e to the x endlessly. Polynomials act similarly. The derivative of x squared steps down to 2x, then 2, and finally 0, a finite set. Trigonometric functions like sine and cosine perform a strict binary toggle under differentiation. The math through line here is structural stability. These specific function families are closed under differentiation. Their derivatives are always just sums and products of themselves. Because these functions preserve their form, they act predictably when plugged into a linear differential equation. They don't generate infinitely wild new shapes. This geometric predictability is our exploit. It allows us to confidently assume that our particular solution, yp, will share the exact same structural template as the original forcing function. We can prove exactly why this method works by looking at the specific scenarios where it spectacularly fails. We just need a function that breaks that structural symmetry. This slide details the method's strict limitations. Notice the excluded forcing functions, the natural log of x, 1 over x, and tangent. Let's trace the natural log. The first derivative of ln of x is 1 over x. The second derivative is minus 1 over x squared. The third is 2 over x cubed. Instead of a closed loop, it creates an infinite expanding chain of entirely new rational fractions. Because of this generation, it is mathematically impossible to construct a finite algebraic template for yp that could balance all those cascading terms on the left side of the equation. Undetermined coefficients is not a universal tool. It is a highly specialized algorithm that relies entirely on the finite derivative boundaries of a few specific function classes. Let's apply this logic to a concrete polynomial to see the execution in practice. Here's example 1. We have a second-order system forced by the polynomial x squared. Looking at the bottom of the screen, we see the complementary function, yc, has already been found. That half of the superposition theorem is complete. Now we need yp. Since the forcing function is x squared, our template for yp must account for x squared plus all possible lower degree terms generated by its derivatives, an x term and a constant. We establish our template, yp equals ax squared plus bx plus c. Beneath it, we take the derivatives. We substitute these pieces back into the original equation, setting it equal to x squared. Finally, on the bottom line, the terms are meticulously grouped by degree. Now we balance the scale. Left and right matching coefficients must be identical. The right side is 1x squared plus 0x plus 0. Therefore, the left x squared coefficient must equal 1. The x grouping evaluates to 0, and the constants total 0. By equating these grouped terms, we extract a basic system of linear algebraic equations for our unknown constants a, b, and c. Notice the procedural shift. By strictly guessing the structural form, we effectively downgrade a complex calculus problem into a straightforward linear algebra matrix. This template logic requires a strict adjustment when dealing with trigonometric forces. Suppose the external force on our system is a sine wave. If f of x equals sine of x, you might logically guess a template of yp equals a sine of x. But the differential equation contains a y prime component. The moment you differentiate that sine term, it inevitably generates a cosine term. To ensure the equation can algebraically balance both derivatives, your yp template must always include a linear combination of both functions. The correct guess is a cosine x plus b sine x. Anticipating the inevitable derivatives of the forcing function, whether they step down like a polynomial or toggle like a sine wave, is the strict requirement for structuring a valid template. Returning to our polynomial example, we can complete the final assembly. After solving the linear system from our equated coefficients, we establish the exact values for our previously undetermined variables. Here we see the results. A is negative 1/2, B is negative 1/2, and C is negative 3/4. We plug these directly into our yp template. Dropping to the final assembly, we execute the superposition theorem. Y of x equals our complementary function, yc, plus our particular integral, yp. We have the yc terms representing the natural, unforced baseline of the system, appended by the finalized yp polynomial, which represents the exact displacement caused by the external force. This combined function is the singular general solution. It perfectly satisfies both the internal physical constraints of the equation and the continuous external load. The method of undetermined coefficients operates essentially as a mathematical blueprint. It is an explicit exploit of mathematical symmetry. By isolating exactly which function families remain closed and finite under differentiation, we can accurately predict how a system will physically respond to an applied force. This framework allows engineers and physicists to look at the seemingly chaotic behavior of forced differential equations and systematically compress them into a predictable, entirely solvable algebraic state.